Greetings to everyone. In continuation to the last class, today we are going to discuss applications of DDQ. Coming to the applications of DDQ, DDQ is helpful for oxidation at active CH functions. In the molecules which contain active CH functions, DDQ performs dehydrogenation, aromatization type of reactions, and it is useful for oxidative coupling, and it is also useful for insertion of oxygen. Now let us see one by one how this DDQ reagent is useful in these applications. Coming to the first one, dehydrogenation type of reactions. Here dehydrogenation means removal of hydrogen. Now see this example. In this example you can see here we have benzylic hydrogen, here we have two benzylic hydrogens. So before going to the example discussion, let us see some representation techniques. Here DDQ, this is the structure of DDQ. This can be represented in simply like this: O double bond, Q double bond O. That means this entire C double bond O, this C double bond is represented like this, and this benzoquinone skeleton it is represented as Q. Now, and the partially reduced skeleton, you can write it like this: OHQ O minus, and fully reduced here in this case you can write it like this: Q OH OH. Now, coming to the discussion of this example, this molecule contains benzylic hydrogen. Now, as we have already seen in the last class, DDQ is highly electron deficient and it abstracts hydride ion from benzylic or allylic CH positions. Here we have a benzylic CH. From this position, hydride ion is abstracted. Now, after abstraction of hydride ion, we will be getting benzyl carbocation. And this partially reduced oxide DDQ, this will take hydrogen from alpha to the benzyl carbocationic position. This hydrogen is taken as a proton. And now this CH bond pair of electrons are shifted over here. Thereby in between these two carbons, you will be getting a double bond. And this positive charge is removed. Now you can see there is a double bond formation in between these two carbons here. These two carbons, this new double bond is formed. Now for one double bond formation, here one DDQ molecule is required. So here hydrogen, here one hydrogen is removed as hydride ion, and here another hydrogen is removed as a proton H+. And one molecule of H2 is removed, and you will be getting this molecule. So here in this case, reactant, it is converted into product. So in this case, DDQ is helpful for dehydrogenation. That means removal of H2 molecule in this case. Next, second application, aromatization type of reaction. Now, in aromatization type of reaction, you can see we already discussed in the last class how tetraline will convert into naphthalene. We have discussed the detailed mechanism how DDQ is converting tetraline into naphthalene. Now, some other example, if you see here, this is a 1, 2, 3, 4, 5. 5, 5 dimethyl tetraline. 5, 5 dimethyl tetraline is converted into 5, 6 dimethyl naphthalene. So let us see how DDQ is converting this molecule. And you can see the molecule, it is getting aromatized, okay, aromatic character. Now, this is 5,5 dimethyl tetraline. This contains benzylic hydrogen here. You don't have benzylic hydrogen at this position because we have two methyl groups, no hydrogen is available. This is quaternary carbon. So here you have benzylic hydrogen. Now DDQ abstracts hydride ion from benzylic position. Now you're getting a carbocation. Next, partially reduced oxide, partially reduced DDQ, which is in the form of oxide, abstracts hydrogen as proton. Then this CH bond pair of electrons are shifted over here and you get a double bond. So you got one double bond. Next, this position here, if you see, this position becomes allylic position. And with respect to this double bond, this is allylic and this is allylic CH. So active CH function. Now DDQ abstracts hydrogen from this active CH as a hydride ion. Now you get a carbocation. So this carbocation is a secondary carbocation. Now, adjacent to that carbon, you don't have any hydrogen. So this molecule will undergo intramolecular rearrangement type of reaction where methyl group migrates from this position to this position as a methyl anion. Now, previously it was a secondary carbocation, it will convert into a tertiary carbocation which is comparatively more stable. Now, the partially reduced DDQ, which is in the form of oxide, will abstract proton from this position, and this CH bond pair of electrons are shifted here, and you get the product, that is 5,3,5,6 dimethyl naphthalene. This is what you call, the molecule is getting aromatic character in this case. You got two double bonds in this case. Now for the formation of two double bonds, you see how many molecules of DDQ is required here in this case? One DDQ and here one DDQ. For two equivalents of H2 elimination, you require two equivalents of DDQ. So this is aromatization type of reaction where the molecule is getting aromatic character. A reactant is converting, and a reactant is getting aromatic character with the usage of DDQ reagent. Now, third type of applications, if you see, it is oxidative coupling. Now, this molecule, if you observe, reactant here in this case, it is undergoing cyclization, and it is an intramolecular cyclization actually. It is coupling type of reaction, and this is associated with oxidation. Let us see how this reactant is converting into product. Now, this reactant, it is having benzylic CH, one benzylic CH. And now DDQ abstracts hydrogen from this benzylic CH as a hydride ion, and you get benzyl carbocation. Now, this is just like a nucleophilic addition type of reaction, intramolecular nucleophilic addition. The hydroxy group, which is in acid, now that oxygen, it attacks onto this carbocation, benzyl carbocation, and you get a cyclic skeleton in this case. Now, partially reduced DDQ, which is in the form of oxide, abstracts this hydrogen. Then DDQ is completely reduced, and you get this product. You get a cyclized product. The molecule here in this case, you are removing two hydrogens. Okay, it is an oxidation, and it is a coupling type of reaction within the same molecule. Okay, this is called as oxidative coupling reaction. Now, next type of application, here in this case, insertion of oxygen. DDQ is helpful for insertion of oxygen where you don't have alpha benzylic or allylic carbocation CH positions or CH functions. Now let us see this molecule. It is just like a chromone. Okay. So in this molecule you have a allylic CH. So DDQ abstracts hydrogen from this allylic position, allylic CH as a hydride ion, and you get allyl carbocation. Okay. With respect to this double bond, this position is an allyl carbocation, and you get a partially reduced oxide of DDQ. Now, for DDQ, you don't have adjacent hydrogen in this case. This hydrogen cannot be removed because it is attached to sp2 carbon. So DDQ now, which is in the form of oxide, it attacks onto this carbocation, and this is just like a hemiacetal structure. Okay. Now, next equivalent of DDQ, it abstracts. Now this hydrogen here, you can see this is again a allylic CH. Next equivalent of DDQ in this case, it abstracts hydrogen from this allylic CH position as a hydride ion, and this you can see here in this case. This molecule you can see, you get oxygen, it is DDQ skeleton, and here you got a carbocation in this case. Now oxide of DDQ, it attacks onto this carbon, which is in the form of carbocation. Now you get a acetal type skeleton. Okay. Now we already know that acetols or ketols, when they undergo hydrolysis, okay, you get diols. Now those diols, they undergo dehydration to give carbonyl compound. Similarly here in this case, this molecule, upon hydrolysis you get a diol. This diol, on dehydration you get the product. In the product you can see you got a double bond O in this case. Okay, that is an insertion of oxygen. Oxygen is inserted at the active CH position.